Inverse relations and introduction to logarithms. First thing we're going to talk about is the inverse function. What is an inverse function? If I take a function like f of x equals 5x minus 2, remember that's just y equals 5x minus 2. If I plug in negative 1 for x, I get negative 7. If I plug in 0, y is negative 2. If I plug in 1, then y is 3, and 2 becomes 8. For the inverse function, the roles of the variables get switched. The input becomes the output, and the output becomes the input. In other words, x becomes y, and y becomes x. The inverse table then would look like this. Notice that all the y's became x's in the inverse function, and all the x's became y's. How do you find the inverse function then? All you do is you swap the two variables, and then you solve for y. Let's take this equation as an example. Now I'm going to use y instead of f of x. I'm going to swap the two variables. So it becomes x equals 5y, I'm using y instead of f of x, minus 2. And then you solve for y. Get y by itself. I get students to make mistakes here only because they don't show their steps. I'm going to add 2 to both sides, and 5y will equal x plus 2. And then I'm going to divide both sides by 5. And for the inverse function, I discover that y equals x plus 2 over 5. You could also write that as 1/5 x plus 2/5. Either way is fine. I'm going to leave it like this. We could write that function like this then. F inverse of x, little mark up there means inverse, equals x plus 2 over 5. Let's just prove that this is the inverse function. If I plug in negative 7, I should get negative 1. F inverse of negative 7 would equal negative 7 plus 2 over 5. Negative 7 plus 2 is negative 5, and negative 5 divided by 5 is negative 1. Notice that if I put in an x of negative 7, I get a y of negative 1, just like in the table. Let's check one more. What about f inverse of 8? That would be 8 plus 2 divided by 5, which is 10 divided by 5, which is 2. Notice if I put in an x of 8 in the inverse function, I get a y of 2. And there it is. When you look at the graph of a function and its inverse, it turns out there's always a pattern. Look at the two graphs. F of x is our original graph. That's all the ordered pairs that are solutions to that equation. And there's f inverse of x. It turns out that a function and its inverse are always reflections through the line y equals x, or f of x equals x, every single time. And in fact, y equals x, or f of x equals x, is called the identity function. Quick review here. Remember what an identity is. If I take an operation like addition, 0 is the identity because when I add 0 to a number, nothing happens, has no effect. For multiplication, 1 is the identity because when I take 8 times 1, it's still 8. 1 has no effect. So under an operation, the identity has no effect on any element in a set. Under those conditions, let's think about what an inverse is. The inverse is the number that when you apply it to another number under the operation, you get the identity. So for addition, the inverse of 8 is negative 8. because I get the identity 0. For multiplication, the inverse of 8 is 1/8 because 8 times 1/8 is 1, the identity for multiplication. For functions, if I compose, this is something we'll do soon, these two functions, what I get is the identity, which is y equal x. But always, a function and its inverse will be reflections through the line y equal x. That's the order pairs 1, 1, 2, 2, 3, 3, 4, 4, -1, -1, -2, -2, and so on. For an equation like y equal x squared, f of x equals x squared, to find the inverse, we will swap the two variables, x equal y squared. By the way, this is not a function, even though this is a function. Just because an equation is a function doesn't mean its inverse is a function, and vice versa. But let's solve for y in this thing. To solve for y, I'll take that function, y squared equals x, and I'll take the square root of both sides. Remember that when you take the square root of both sides, like in x squared equals 9, I have to put that plus or minus there because there are normally two solutions. In this case, positive 3 and negative 3, or plus or minus 3. Both of those squared make 9. So I need a plus or minus here. And the inverse of y equal x squared is y equal plus or minus the square root of x. Let's take a look at that on the graph. Here we can see the graph of y equal x squared. That's the parabola. Talking about this one right here. And y equal the positive of the square root of x is this piece. Y equal the square root of x. And down here is y equal the opposite of the square root of x. So these two together make the inverse of the original function. Notice that this sideways parabola is not a function. The rules of a function are that every x must have a single y value. And if I pick any x on the x-axis and I go up or down, if I draw a vertical line, I can see that this x value will have 2 points associated with it. It's not a function. And remember what I previously said, a function and its inverse are reflections through the line y equal x. Here's that same graph again, but notice, here's my original equation, the parabola, y equal x squared. Desmos doesn't care whether or not it's a function. Our graphing calculators can't handle this, but Desmos can. You can actually just punch in x equal y squared, which is not a function, and Desmos can handle it just fine. So this is x equal y squared. Note how they're reflections of each other through y equal x? That's what happens with a function and its inverse. And finally, we get to the logarithm. What is a logarithm? It is the exponent to which a base is raised to obtain a value. If we take an exponential equation like y equals b to the a, this is equivalent to the log base b. Now remember what I said, a logarithm is an exponent. The exponent is a, it's equal to a. The log is equal to an exponent. This becomes then the log base b of y equals a. These two things mean the same thing and are interchangeable. If I knew that the log base m of n was equal to z, this would imply the base. Remember that in an exponential equation, the bottom number, like right here, is the base. So this is the base, and this is the base of the logarithm. The log base m of n equals z. The log is an exponent, so the exponent is z. M to the zth power equals n. These two equations are equivalent. Let's throw some numbers in there. I know that 3 squared is 9. If I was to write that as a logarithmic expression, it would be the log, the base is 3, the exponent is 2, the log is equal to an exponent of 9. The log base 3 of 9 equals 2. Those two are equivalent. Notice how this is base 3. Your calculator has a log button, and if there is no base, the base is 10. If I had an expression like 10 cubed equals 1,000, I can write that as a logarithmic expression. It would be the log base 10, the base is the bottom part of the exponential expression. It's equal to an exponent, which is 3. So the log base 10 of 1,000 equals 3. Try this in Desmos. Here I plugged in the log of 1,000. What I said was if you don't put a base, automatically the base would be 10. So the log of 1,000 is 3 because 10 to the third power is 3. 2 to the fourth power equals 16. Could be written as the log. The base is 2. It's equal to an exponent, which is 4. And then it would be the log base 2 of 16. That would be 4. And there's a way to change bases. We'll talk about that later. But let's take a logarithmic expression and make it an exponential expression. The log base 7 of 49 is equal to 2. And that's because the base is 7. That's the base of the logarithm. 7, the log is an exponent to the power of 2 is equal to 49. Sometimes you might see some weird fractions when you work with logarithms. I'm going to point this out for you. When you say the square root of 64, there's actually a little 2 that we don't write. It's not the 2 in front. It's not 2 root 64. It's a little tiny 2, which just means the square root of 64. Just like we can say the cube root of 8. We don't write that 2 with the square root because it's understood to be there. But that'll help you understand what I'm doing here. It turns out that this is the same thing as 64 to the 1/2 power, which is of course 8. And the cube root of 8 then is actually 8 to the 1/3 power. And the cube root of 8, what number times itself 3 times makes 8? It's 2. 2 to the third is 8. And the fourth root, I'm doing ones I know here, of 81, as an example, is 81 to the 1/4. That'd be the number times itself 4 times makes 81, and that would be 3. 3 times 3 times 3 times 3, 4 times makes 81. And you can keep going with this. I could do the fifth root of 32. That would be 32 to the 1/5 power, which is in fact 2. 2 times 2 times 2, 5 times makes 32. Then you can get something like this too. You can say the fifth root of 32. Notice that 5's up top. It's not in front. I made it a little bit big there. Cubed. That would be 32 to the 1/5 power cubed, which is the fifth root of 32 cubed, which by the way is 32 to the 3/5. The fifth root of 32 is 2. We already figured that out. And 2 cubed would be 8. Try it on your calculator. Try it in Desmos. 32 to the 3/5 power is 8. So what you need to observe here is that the bottom number in that fraction is the root, and the top number is the power you're going to take it to. So that's a normal old cube up top. I can apply this to logarithms and say the log base 16 of 4 would equal 1/2, and that's because 16 to the 1/2 power, remember 1/2 is just a square root, is 4. And if I said 27 to the 1/3 power, that's actually the cube root, that is 3. Cube root of 27 is 3. I could write that as a logarithmic expression, would be the log base 27. Remember, the log is an exponent. It's equal to 1/3. The log base 27 of 3 equals 1/3. So what's the big deal about a logarithm? Why are we learning about logarithms? Well, let's talk about the inverse here. Inverse. Remember what we do with the inverse is we switch the variables. We make it x equals b to the y, and we solve for y. How do we solve for y? Well, what is a logarithm? The log, look at my expression, the bottom number, the base is b, and the log is equal to an exponent, so this is equal to y. That means the log base b of x equals y. All right, look right here and look right here. These two are inverses of each other. The logarithm is the inverse of an exponential equation. Let's take an equation like y equal 2 to the x and find its inverse. Swap the variables. It becomes x equals 2 to the y, and then we'll put that in logarithmic form. This is the log. The base of my expression is 2. The log is equal to an exponent. That's y. The log base 2 of x equals y. And let's look at these two graphs in Desmos. Aren't they beautiful? Perfect reflections of the line through y equal x. What this means is that we now have the ability to solve for an exponent. This is just a simple example of what I'm talking about. I could find x, yeah, I can guess and check, or maybe you recognize patterns and can figure it out, but let's just point out that what this is as a logarithmic expression is the log base 10 of 100,000 is equal, the log is always equal to an exponent, it is an exponent, x. And because base 10 is the standard, I can just plug this in the calculator and I'll know what x is without having to guess and check or notice patterns. And we can, of course, do this with any exponential expression, and that's what we're headed towards. The rest of this video is questions from your assignment. A lot of these just take seconds. This first one is a great example. Some values of an invertible function, that just means it has an inverse, f, are given in the table. Complete the second table of values for f inverse. With the inverse function, the roles of the variables are exchanged. We swap the variables. In a table, all we do is swap the values. The x's become the y's, and the y's become the x's. So for the inverse function, we'll just take these x's, which now become y's, and copy them down. 2, 3 becomes 3, 2. Very tricky here. They rearrange the order. 2, 3 becomes 3, 2 in the inverse. Oh, that's right there. 3, 6 becomes 6, 3. Haha. And 4, 2 becomes 2, 4. And 5, 4 becomes 4, 5. And 6, 5 becomes 5, 6. Changing the order, that was very sneaky. In question 2, we have an invertible function. That means it has an inverse. And they're given by this table. Find f inverse of 432. Looking right here in the original equation, f of 3 is equal to 432. That means for the inverse, the roles switch, the variables switch. F inverse of 432 would equal 3. So the answer here is 3. Question 4. Use the table below to fill in the missing values. F of 6, this is the original equation. F of 6 would equal 3. If f of x equals 1, don't forget that f of x is just y. This is the normal equation. If y is 1, look at the table here and look for y values. Right here is 1. If y is 1, we know that x is 3. F inverse of 3. Now, this is the inverse function. And the inverse function, remember, these variables are switched. So this is actually right here a y value in the original equation. We could make an inverse table if we'd wanted. We'd have, this is be f inverse of x, and my x and my y values. Remember, they would be 5, 0, 6, 1, 7, 2, and so on. So this is a y that becomes an x. Remember, this is f of x, but now I'm talking about the inverse function. It's actually a y in the original table. And in the original table, we can see that y was 3. That'll be an x here. It'll be 3, 6 when we get there. And yes, this is 6. If f inverse of x equals 3, we're saying if y in the inverse function equals 3, now, y in the inverse function will be x in the original function. So if the y value is 3, there we go. I didn't copy that down far down in the table. 7, 2, that was from right there. The next one would have been 1, 3, because I skipped down to create that one. So when y is 3 in the inverse equation, we know that x would be right here, 1. If you get confused by this, because it is a little confusing, what my suggestion is to take this table and make an inverse table by just switching all the x's and y's and then answering the question. Question 5 is a quick one. Here's a table for a function f of x. Choose the table below. There's the inverse function. The x's become the y's become the x's. 3, 1 here becomes 1, 3. 4, 6 becomes 6, 4. 8, 9 becomes 9, 8, and so on. Looks like it's this one to me, right here. Here we're given a graph, and we're supposed to find the inverse graph. Easiest way to do this is just pick a couple of points. How about this one? This is 0, -2. And this one, 1, 1. Now for the inverse function, we know the inverse will have 1, 1 when I switch the two. This is f inverse of x. But it will also have -2, 0. And of course, you can pick some other points. But look down below here. It's going to have to hit -2, 0. -2, 0. Well, the only one that does that is this one right here. It also has to hit 1, 1, which is that one. Hey, you found it. Question 10. Graph the inverse of the given function on the same set of axes. Pick a couple of points. It can be any 2 points on the line. This one looks like it would work. And this one looks like it would work. This would be the point 5, -5. And this would be the point -4, -2. F inverse of x then, those will be swapped. -4, 2 will become -2, -4. And 5, -5 will become -5, 5. So we'll plot those 2 points. -2, -4. Kind of right there in the way. I'll change colors. Right there. And -5, +5 is right there. That looks pretty good. We can check this by drawing in the line y equal x. That's 1, 1, 2, 2, 3, 3, 4, 4, negative 9, negative 9. Do those two lines look like the reflection through y equal x? I'd say it's pretty good. Here we're going to plot the inverse of the function shown on that grid. Let's take some ordered pairs. This one is negative 6, negative 5. And every time it changes, I'm going to do another ordered pair. That would be negative 3, negative 2. And right here we have negative 2, 2. And this last one will be 1, 4. And there'll be an open circle right there at 1 for the inverse function. Let's plot these points. 1, 4 becomes 4, 1. Negative 2, 2 becomes 2, negative 2 for the inverse. This is f of x, and this is f inverse of x. Negative 3, negative 2 becomes negative 2, negative 3. And negative 6, negative 5 becomes negative 5, negative 6. I plotted those points, and I put an open circle for the point 4, 1. You can't put those two on one graph very easily, but do those look like reflections to the line y equal x? I'd say yes. These questions are very quick. Just be sure that you're careful about your work. I always get students that make silly mistakes solving these things. We're going to find the inverse function, and we're going to take the function y equal 8 minus x, and we're going to swap the variables to find the inverse function. X equals 8 minus y. Then we're going to solve for y. We'll take an 8 off each side. I'm going to turn this around. Negative y equals x minus 8. Then let's need to divide everything by negative 1. And it looks like f inverse, this is my y, equals, and I'm going to take and divide both of those by negative 1. That'd be negative x and positive 8. Negative x plus 8. Our equation on number 14 is y equals 12x plus 3. To find the inverse, we'll switch the variables. X equals 12y plus 3. We'll take a 3 off each side. X minus 3 equals 12y. We're getting y by itself. Divide both sides by 12. And y will equal x minus 3 over 12. Now I'm going to check here. You could also write this as 1/12 x minus 3 over 12, which would be 1/4. So these two equations are the same equation. I'll check and see if it handles it both ways in WAMAP. And the answer is yes. WAMAP will accept either answer. They are equivalent. Question 15. We'll exchange the variables. X equals 1 over y plus 12. I guess I put this over 1 and cross multiply. And we get x times y plus 12 equals 1 times 1, 1. I'm going to get y by itself. I'm going to divide both sides by x first. And we get y plus 12 equals 1 over x. And we'll just take a 12 off each side. And we get, I'm going to take y here and make it f inverse of x. That's the inverse function. It would be 1 over x minus 12. Here's an interesting question. We have y equal 11 plus the cube root of x. We'll switch the variables, swap them. X equals 11 plus the cube root of y. We're going to solve for y. We need to get this by itself. It'll be the cube root of y equals, I have to take 11 off each side, x minus 11. I flipped it around. To eliminate that cube root, we need the inverse of a cube root. Inverse of a cube root is a cube. The inverse of a square root is a square. The inverse of a fifth root is a fifth power. So we'll take the cube root of each side, and this gets y by itself. And y will equal x minus 11 cubed. I hope they don't make us FOIL that. We'll check it in WAMAP. Good news, they don't. This is the answer they have. Let's find the inverse of that function. We'll swap the variables. X equals y plus 1 over y plus 9. Notice that we have y's in two spots. We're going to have to find a way to get y by itself. To do that, I'm going to put this x over 1, and then I'm going to cross multiply. I'm going to take 1 times y plus 1, which is y plus 1, and on the other diagonal, I'm going to take x times y plus 9 and distribute. That'll be xy plus 9x. Let's get the y's on one side. We'll move the xy over here and move the 1 over on the other side. So subtract xy from both sides. This becomes y minus xy. And subtract 1 from both sides. This becomes 9x minus 1. Notice right here that y is in two terms. We've got a greatest common factor of y. We're going to undistribute that y. We get y times 1 minus x equals 9x minus 1. Now we'll divide both sides by 1 minus x. And that cancels, and I can see that f inverse of x, that's what y is 9x minus 1 over 1 minus x. To finish this equation, we're going to find f inverse of negative 1. This is the x we're going to plug in. That is 9 times negative 1 minus 1 over 1 minus negative 1. This is negative 9 minus 1, which is negative 10, over 1 minus negative 1 is 1 plus 1, which is 2. So this is negative 5. F inverse of negative 1 equals negative 5. The rest of these questions should go quite a bit quicker. Convert from exponential form to logarithmic form. This is equal to the log. The base is the same as the base of your exponential expression. The log base 3. Log is equal to an exponent. The exponent is 2. Every log is an exponent. It's always equal to an exponent. So log base 3 of 9 equals 2. The second one would be the log base 9. Again, it's equal to an exponent, 3, and that would be 729. This is the log. The base is the bottom part there, base g. It's always equal to an exponent, which is h. And is that a b? And then the last one is the log base b equal to an exponent, which is h of g. 22, this is even faster. Write this logarithmic expression as an exponential expression. The base is 4. The log is always equal to an exponent, so it's 4 to the third, and that equals 64. The second one, the base is 3, and the exponent is 2, because the log is an exponent. That's equal to 9. And the last one, the base is 2, the exponent is the 5, and that's equal to 32. 2 to the 5th equals 32. Here we have some of those fractions mixed in. Remember that the square root of x, or the square root of 100, is the same thing as 100 to the 1/2 power. I explained that in the teaching part. If you missed it, go watch it again. The cube root of 8 is the same thing as 8 to the 1/3. Those are identical. Let's write this as an exponential expression. The base of the log is 16. The exponent is what it's equal to. It's always equal to an exponent. 16 to the 1/2, that's really a square root. Square root of 16, and that equals 4. The second one there, the base is 16, and this is your exponent because the log is equal to an exponent. 16 to the 1/4, that's the 4th root of 16, which is 2. 2 times 2 times 2, 4 times makes 16. And the last one, the base is 27. The exponent is 1/3. This is a cube root. The cube root of 27, that's 3. We'll convert these to logarithmic expressions. The base of the log is the base of the exponential expression, the log base 81. You know the log is equal to an exponent, which is 1/4. And the log base 3 of 81 then equals 1/4. The second one, the log is base 4. The exponent is 1/2. It's always equal to an exponent. And the log base 4 of 2 is 1/2. The last one is the log base 64. The exponent is 1/3. So the log base 64 of 4 is equal to 1/3. Another super fast one. We'll write this in exponential form. This is the base of u. The log is an exponent, so the exponent would be t. U to the power of t equals m. There's your answer. In question 28, we're going the other direction. This is the log. The base is the base of the exponential expression, which is 6. The log is an exponent, so it's equal to m. The log base 6 of u then equals m. And here is where we're talking about how the logarithm is the inverse of an exponential function. This is the equation y equals 4 to the x. To find the inverse, we flip the role of the variables. It becomes x equals 4 to the y. To make this an expression that we can actually work with, we write it as a logarithm. This is the log. The base is 4. The log is an exponent, so it's equal to y. The log base 4 of x then equals y, which means f inverse of x, this is y, is equal to the log base 4 of x. And our last one, find the inverse of this function. This is y equals the log base 5 of x. To find the inverse, we'll swap the variables. X equals the log base 5 of y. And we'll write this as an exponential, equivalent exponential expression. The base is 5. The exponent is x because the log is equal to an exponent. 5 to the x equals y. In other words, y equals 5 to the x. And y is the inverse function. So f inverse is 5 to the x. F inverse of x is 5 to the x.